Welcome. So in this video, we're going to go over a quick intro to open addressing. So if you guys remember, open addressing was one of the ways that we could actually write our hash tables, and it solves collisions in our hash tables by the use of probing. So in this case, let's assume that we're actually running an event where we have 1,000 seats possible, and it just so happens that John Smith and Sandra D um, somehow ordered their tickets around the same time, and they both got tickets for seats 873. So the issue here is, how do we actually fix this? Because we can't have John Smith and Sandra D sit in the same chair, and we're probably not going to have Sandra D sit on John Smith's lap, because they probably don't know each other. So the idea here is, okay, we take a look. We notice that John Smith ordered his ticket a split second before Sandra D did. So it's only fair that we give John Smith the 873rd seat. Now, what we do for Sandra D, she's going to be upset if we don't give her a seat. So what we're going to try to do is give her the next available seat. So in this case, we check the next seat over, and we see if it's open. And in this case, it happens to be open, so we place Sandra D there. So that's what probing is going to do. Probing is just going to find the next available spot in case we have a collision. So let's take a look at the pros and cons of open addressing. Open addressing is fast on very small data elements, but it's terrible with large data files. The reason why it tends to be terrible with large data files is because we continually have to resize and rehash things over and over again. We can also have a thing called primary clustering, which is where we have big hash blocks, meaning that our data is not evenly distributed amongst the hash table, and it's pretty bad. So the pros of our open addressing over a separate chaining is that we only use a single data structure, which is going to be an array, while in separate chaining we use an array and we also use linked lists. And the nice part about open addressing is it's not too hard to implement. So let's talk about linear probing. So the idea of linear probing is it's saying that if our hash spot isn't empty and the spot that we're currently looking at happens to be where we've originally hashed to, what we want to do is we want to move to the next and update our hashing spot here. If we've moved beyond the extension of the end of the array here, then what we're doing is we're wrapping around to the very beginning and just kind of continually looking. Now this keeps going up until either we find an open bucket or open seat, or we find that we've kind of went through the whole thing and failed to find an open space. So once again, it can lead to a large cluster of hash blocks if everything keeps hashing to the exact same value, or everything that gets hashed tends to hash into something that's already been filled. So the runtime of the hash in the worst case could be linear, which is not very good. So we can try to improve this with quadratic probing. So what quadratic probing does is it says, okay, we're going to take a look at our current hash spot, and while we haven't actually filled this data, or we haven't found an open bucket for this data, what we're going to try to do is we're going to try one step away from our current hash spot to see if that bucket's open. If that doesn't work, we try 4 steps away from our original hash spot. If that doesn't work, we try 9 steps away, etc. So the idea here is that if our table size is prime and the table is at least half empty, then quadratic probing will always find a spot for our data element. And then the reference that I used was the Data Structures and Algorithm Analysis book by Mark Allen Weiss to make these slides. So let's actually take a look at the implementation of a hash table here. So in the hash table, we have our load factor, which is always going to be final, so it's never going to change. Default capacity is never going to change, it just starts the initial size of our table. Size keeps track of basically how many elements we have so far. The table we're going to be hashing strings, so it makes sense that we're using a string array. So the constructor is pretty self-explanatory. Our insertion method here it calls our hash function and passes in the value. So we try to find the appropriate value to hash to, and then once we find that spot, we just place our value in there and we increase the size. So the idea is if our load factor has been breached, then what we do is we call a rehash. So our delete method here basically tries to find the appropriate hash value and then set that position to null. And then what we do eventually is we decrease the size here. So our searching algorithm, it once again calls our hash, passes in our string. So this might seem a little weird, like how is our search and how is our delete going to appropriately get the proper hashing value when we could have multiple collisions? Well, we'll get into that right now. So this is a little bit of a modified version of the hashing function that Mark Allen Weiss displays in his data data structures and algorithm analysis book. So the only difference is that I have hash code equal to this function, whatever this function returns, which is called linear probe, which takes in a hash code and then our hash string. So let's take a look at linear probe. So for linear probe, we set our original probe index to be equal to the hash code that we currently have. And then what we try to do is we try to find a space that's empty, and then we also try to see if we don't have any duplicates, because if we have duplicates in our hash table, it's probably not going to be useful as far as things go. We don't want to hash the same save states of a game over and over and over and over again, because that would be a bit redundant. So what we need to do is if we happen to get inside of this if condition, we already know that the position that we're at is not null, meaning that our bucket is full at this spot, and then our string happens to be unique. So what we're going to do is set our probe index to be the next bucket over. And what we're going to do is we're going to check to see if that bucket is empty, and make sure that our probe index is not equal to our original hash code so that we haven't looked through everything. And then we have another safe check here. We want to make sure that the current spot we're looking at is not equal to the string. So if any of these conditions happens to fail, then we immediately break out. So this right here is one of the ways that our search and our delete methods are going to be able to find the appropriate string values that they're looking for. And once again, after that, it just works the way that linear probe would, where it keeps incrementing the probe index over and over again. And then if we happen to breach the table length, then what we do is we start at the very beginning again. So in the event that we've kind of gone through everything here, and our probe index happens to be equal to our hash code, it basically means that at this point we've searched through our entire array and we haven't found an actual position, and we failed. So the reason why I have this check here and the reason why it throws an illegal state exception is because if we've gotten to this point, it means that our rehash function was never called because our load factor was probably failed. So this is bad. This never happens. This never should happen. So, and at the end we return the probe index. So let's take a look at rehash. Rehash only occurs whenever we breach our load factor, which is basically almost 70% of the actual table size. So what we want to do here is we keep track of our old table, and then we set our new table to be equal to a new empty string array that's going to be double the size of our old table. And then what we do is we just continually loop through all the values in our old table, and then we hash those values into our new table to the appropriate spots in our new table, taking into consideration the length of our new table. So, and once again, size stays the same. The size of elements or the number of elements that we have does not change in this function. It only changes whenever we insert something or delete something from our table. So hopefully that all made sense to you guys, and see you next time.